Okay, good evening students. Now we will see the noise analysis part. In that we already covered the noise analysis of the analog communication system. Now we will see how the noise affected in the digital communication system. Now you tell me, what is the noise analysis of analog communication system? What are the parameters you are calculated in the noise analysis when it is affected in the analog modulation techniques or analog communication system? The performance of the noise in the analog communication system by a parameter, by a measurement, you are calling it a signal to noise ratio. Okay, the signal to noise ratio is the parameter or a performance indicator of analog communication system with respect to noise. So in an analog communication system, now how much is the signal to noise ratio of AM, FM, DSB, SSB, all these things we already covered. Because now that is a continuous wave signal. Now there we are finding every time there is a chance of continuously the noise is affected. So you call it as a signal to noise ratio or figure of merit. Those are the performance indicators. For a best communication system with respect to noise, a signal to noise ratio should be as high as possible. That is about the analog communication system. Now what about this digital communication system? Now here the digital communication system is nothing but in terms of binary ones and zeros. Now we are transmitting binary 1 and my receiver is receiving binary 1. I am transmitting binary 0, my receiver is receiving binary 0. So which is very good. Whatever we are transmitted, the reception is also the same. So there is no error, right? Now here error is 0. But now the same case, now I am transmitting binary 1 but the received is 0. I am transmitting binary 0 but the received is binary 1. Then there is an error taking place. Is it right or not? Then the chance of error. So when binary 1 is transmitted, binary 0 is received. Binary 0 is transmitted, binary 1 is received, then error will take place. Now the question is, how much probability such that the receiver will do a mistake? Now that is called it as error probability of error. That is called as a probability of error, or also called as bit. Now while transmitting bits, error is taking place. Therefore this is called as bit error rate. Probability of error or bit error rate, both are same. Okay. So these are the performance indicator while a digital data is transmitted. So in terms of binary ones and zeros, now how many bits are going to be an error? The receiver will receive how much bits with how much error probability. Now we are going to be calculated. Now you tell me the error probability in analog communication system, the signal to noise ratio should be as high as possible. Now in the same manner, in the digital communication system, the error probability, your expected error probability is 100 or your expected error probability is 0. Yes, obviously we want the probability to get the error should be as minimum as possible. So we are expecting the minimum error probability such that the receiver is a good receiver, that digital communication system is a good communication system. Okay. Now where the effect of noise is less in the case of digital system. If the error probability is more, a more chance of error. So more error means more noise. Noise is dominating and your signals get disturbed. Okay. So now we will see first of all how to calculate the error probability, and that error probability depends upon what parameters of a digital communication system. So now first what we are treated as, now here I just take in the presence of noise. In the presence of noise, we are transmitting. In the presence of noise, we are transmitting binary 1 and binary 0. So what we are doing is, in the presence of a noisy environment, in the presence of a noisy system, now we are transmitting the binary ones and binary zero. So even in the noisy environment, how strong my binary data is reproducing, how strong my binary zero is reproducing. Okay. So now in the presence of noise, only noisy signal. Am I right or not? Now you tell me, now in the presence of noise means only noisy signal. Now what is the probability density function of noise? The probability density function of noise is, you know the properties of noise. Probability density function of noise is Gaussian distribution, Gaussian distribution, Gaussian distribution with zero mean, right? With zero mean. So what is the probability density function of Gaussian distribution with zero mean? Now f of x, which is equal to 1 divided by root 2 pi sigma square e power minus of x minus mx whole square by 2 sigma x square. This is the probability density function of a Gaussian distribution with mx as a mean, sigma x square as variance. But here I am talking about not a signal, I am talking about a noise. But for noise, therefore I just represented this is n. This is the probability density function of noise, sigma n square, mn square. Now this is sigma n square. But you know that what is the mean of thermal noise? The mean of thermal noise, which is equal to 0. Therefore fx of n, which is equal to 1 divided by square root of 2 pi sigma n square into e power minus x square, mean is 0, mn mean is 0, and this is a noise, right? Now this is the noise signal. Let us assume only a noisy environment. E power minus n square by 2 sigma n square. This is the probability density function of noise with zero mean. Now which is a Gaussian distribution with a zero mean and sigma n square as variance. With a zero mean and sigma n square as variance. Clear or not? So under this noisy environment, now we are transmitting binary ones and zeros. Now how the behavior of the noise in the present, how the behavior of the signal in the presence of noise, we will see, and how much is the error, and what should be the probability of that particular error, and what should be the chance of bits will make it error is called as bit error rate. All these things we are calculated. First you note down. Right, now this is the probability density function of noise with a zero mean Gaussian distribution, right? Now under this noisy environment, now we will take case 1. What is the case 1? Now signal A1 is transmitted. Signal A1 is nothing but binary 1, bit 1. Signal A1 is transmitted. So now you tell me, now signal A1 is transmitted. Now the X is a random variable which is used to represent the noise. Signal A1 is transmitted. You know that what is the property of thermal noise? The one of the property of thermal noise is additive in nature. Therefore, the noise is always added to the signal. Now X of n, which is equal to A1 plus n, the noise is always added to the signal. Therefore, now this is the probability of thermal noise. Therefore, noise which is equal to X minus A1. Can I write like this? Noise equal to X minus A1. X is the random variable. When a signal A1 is transmitted, the noise is added to the signal. Therefore, if I substitute here, then what is the probability density function? Now the probability density function of noise when signal A1 is transmitted, which is equal to 1 divided by root 2 pi sigma n square into e power minus of x minus A1 whole square by 2 sigma n square. X minus A1 whole square by 2 sigma n square. Now this is the probability density function . Now see here. Now this is the probability density function of a noise under Gaussian distribution. Now this is X is a random variable which is used to represent the noise. Now when binary 1 is transmitted, right? When binary 1 is transmitted, now see here, now what is the mean? Mean is A1. This is a A1 is mean. Earlier it is 0. Now this is A1, signal strength. Now this is A1. Now which is a Gaussian distribution. Now this is the probability density function of noise when signal A1 is transmitted. This is for binary 1 or bit 1 is transmitted, right? Now similarly, now we'll take both two cases. Case 2. Now signal A2 means binary 0. Signal A2 is transmitted, means binary 0 is transmitted. Now what is the probability? The random variable which is represent the noise. Now when A2 is transmitted, the properties of the thermal noise is additive in nature. Therefore, the noise is coming and added to the signal. Therefore, here I can write X equal to X minus A2. Now what is the probability density function of noise when signal A2 is transmitted, which is nothing but 1 divided by root 2 pi sigma n square into e power minus of X minus A2 whole square by 2 sigma n square. Now binary 0 is transmitted. This is also a Gaussian distribution, but now A2 is transmitted. Now this is A2 is transmitted. Now bit is 0. Now this is the intersection. This is nothing but the threshold voltage or not? Now this is the average voltage levels for binary 1 and binary 0. The average voltage levels represented for binary 1 and binary 0 is called as threshold voltage. Now let us take this is lambda naught threshold voltage. Now what is the lambda naught? Which is equal to A1 plus A2 by 2. Now this is threshold voltage, or we call it as a threshold set. Threshold voltage or threshold set. Now see here. Now what we want to calculate here? We want to calculate how much is the error probability, right? So now what I am doing is, now listen carefully. Now when a random variable x lies between minus infinity to lambda naught. Now this is the area, minus infinity to lambda naught. Now this is area. Now when this area signal A2 is transmitted and signal A2 is received, then what is the error probability? No, because when a random variable x less than lambda naught, it belongs to binary 0, it belongs to A2, therefore then the error probability is 0, which is good. But now see here, then the other case, the random variable x lies between lambda naught to infinity. This is greater than lambda naught. Okay, this is greater than lambda naught to infinity. Now when signal A2 is transmitted, A2 is received, error probability is A1. Error probability is 0, because when the strength greater than lambda naught is treated as binary 1, strength less than lambda naught it is treated as binary 0, so error probability is 0. But now let us assume the error will be taking place when a random variable x greater than lambda naught and less than infinite, but now signal A2 is transmitted. Now when signal A2 is transmitted, definitely the error will taking place. Am I not? Now, but this is the region which is allotted for binary 1, but you are received a binary 0, therefore then the error will takes place. Error will takes place, and that error is how much? And that error is how much? What should be that error probability? Now we need to calculate. So I want to take this and such that what should be the error probability, and it depends upon what parameter. Okay, note on this. Now there is a relation between probability and probability density function. When a random variable x lies between lambda naught to infinity, which is integral lambda naught to infinity, probability density function when signal A2 is. This is the relation between a random variable x lies between x1 and x2, the relation between probability and probability density function. So that is the error probability we need to calculate. Now the error probability when a random variable x lies between lambda naught to infinity, which is equal to integral lambda naught to infinity, now fx of a2 into dx. Now which is nothing but integral lambda naught is how much? A1 plus a2 by 2. F of x is 1 by root, this is f of x, root 2 pi sigma n square is outside sigma n, e power minus of x minus a2 whole square by 2 sigma n square. Now this is the probability of error. Now the probability of error, which is equal to 1 by root 2 pi sigma n integral a1 plus a2 by 2 infinity e power minus of x minus a2 whole square by 2 sigma n square into dx. Now that is the error probability we need to calculate and depends upon what parameter. So now we'll converted this error probability into Q function. Now there is a Q function here, if you observe, this is the Q function which is equal to 1 by root 2 pi integral x to infinity e power minus gamma square by 2 into d gamma. Now this is the error function. So let us take, so there may be a similar to this one, and we converted this equation to that. Therefore let us change the limits. So let us assume first e power minus gamma square by 2. Therefore let us assume gamma, which is equal to x minus a2 by sigma n, right? Such that this is e power minus gamma square by 2. Now let gamma equal to x minus a2 by sigma n. Therefore let us first lower limit x equal to a1 plus a2 by 2, then it will convert it to gamma, which is equal to gamma equal to a1 plus a2 by 2 minus a2 by sigma n. Therefore this is nothing but a1 minus a2 by 2 sigma n. Now upper limit x equal to infinity, such that gamma equal to infinity minus a2 by sigma n, infinity minus something which is equal to infinity. Therefore, and this is d gamma, differentiate d gamma by dx, which is equal to 1 by sigma n dx is 1 minus 0. Now let us differentiate this. So from here we can get that dx, which is equal to sigma n into d gamma, dx which is equal to, therefore all limits are converted in x to gamma, so you can substitute here, which is equal to 1 divided by root 2 pi sigma n. Now what is the lower limit? a1 plus a2 by 2 will become a1 minus a2 by 2 sigma n. Now upper limit infinity will become infinity. Now this is e power minus gamma square by 2. X minus a2 by sigma n is gamma, e power minus gamma square by 2. What is dx? Dx is this. Therefore what is dx? Dx is nothing but sigma n into d gamma. Therefore this sigma n cancel. Now let us take here. Then this will be same as that of Q function or not? 1 by root 2 pi integral a1 minus a2 by 2 sigma n infinity e power minus gamma square by 2 into d gamma. Now you just compare. Now 1 by root 2 pi, 1 by root 2 pi, infinity, infinity, e power minus gamma square by 2, e power minus gamma square by 2 d gamma. But what is the lower limit? Now this is x, therefore this is q of x. Therefore this is a1 minus a2 by 2 sigma n. Therefore this is nothing but q function of a1 minus A2 by 2 sigma n. This is the probability of error in terms of Q function. Okay, note down. So finally, what is error probability in terms of Q function? Now the probability of error which is equal to, in terms of Q function, Q of A1 minus A2 by 2 sigma n. This is the final answer you are getting, right? So now let us see here. I just give in another way. Probability of error which is equal to Q of X, right? This is Q of X. So now you see here, if you take this as example, as X increases, as X value is increases, right? Because these are all are fixed. As X increases, now this Q of X is what happen? Decreases, because this X is inversely proportional to Q of X. As this X increases, Q of X is decreases. Am I right? Why? Because now I want minimum probability of error. If you want a minimum probability of error, Q of X is minimum. Am I right? Now see here. If you want minimum probability of error, if your Q of X is also minimum. But when this Q of X is decreasing, when this X is increasing. Therefore, error probability is minimum when Q function is minimum. This Q function is minimum when this X value is maximized. So this X is maximized. So we want a maximum value of X. We want a maximum value of X such that Q of X is minimum, such that probability of error is also minimum. But what is X here? The X is nothing but A1 minus A2 by 2 sigma n. Therefore, maximize the value of A1 minus A2 by 2 sigma n. Maximize the value of A1 minus A2 by 2 sigma n. Now for getting maximized value, you just square it. Energy, maximum in square, energy. A1 minus A2 by 2 sigma n whole square, which is nothing but A1 minus A2 whole square by 4 sigma n square, which is nothing but this A1 minus A2 whole square, will write it as ED. What is ED? ED is the energy difference between the signal. ED, which is nothing but energy difference between the signals. Energy difference between the signals. Why? Because this is one binary 1, this is binary 0. Now this is A1 minus A2 whole square. Therefore, the energy difference between the signals, ED, which is equal to, can I write like this? Now each bit is having a duration of TB, bit duration TB, which is nothing but x1 of t minus x2 of t whole square dt. Or this is one signal S1 of t and this is another signal S2 of t minus is energy difference whole square dt. Okay, this is energy difference between the signals. Okay, so now this is ED by 4 sigma n square. What is sigma n square? Variance of thermal noise. Now you already know the property of the thermal noise. Now what is the variance of thermal noise? Which is equal to N naught by 2. the variance of thermal noise, which is nothing but the power spectral density of the thermal noise, which is N0 by 2, therefore which is nothing but ED by 2 N0. Therefore, now what is this? Now the maximum value A1 minus A2 by 2 sigma n maximized value, which is nothing but this is underscore square root. Now maximum value is nothing but square root of ED by 2N0. Now this is A1 minus A2 by 2 sigma n, which is nothing but this square will go to that side under root. So this is A1 minus A2 by 2 sigma n, now which is nothing but square root of ED by 2N0. Now which is nothing but, now what is error probability? So the error probability finally ultimately the error probability, the minimum error probability, which is nothing but Q of, now maximize the value of x, which is nothing but square root of ED by 2N0. Here is also you can understand, so the error probability is depends upon energy of the signals, energy of the binary 1 or binary 0's difference by noise power spectral density. This is the noise power of thermal noise. Okay, so this is the noise, this is the signal strength. Energy is nothing but this is the signal strength, this is the noise. Now there the signal to noise ratio, here is also this is the energy signal strength, this is the noise. This is the error probability. The error probability is definitely depends upon the signal strength and the effect of noise. Okay, note on this. Now we will calculate the probability of error of all the given signals. This is the probability of error or bit error rate, probability of error while the bits are transmitted, and how much is the error rate of the bits. So bit error rate or probability of error. Now see here. Now energy difference between the signal. Now we will calculate one by one. ASK, amplitude shift keying error probability. What is amplitude shift keying? For binary 1, S1 of t is A cos 2 pi FCT. For binary 0, S2 of t is which is equal to 0. For binary 1, this is for binary 0 this much. Okay. For binary 1, A cos 2 pi FCT. For binary 0, 0. Amplitude shift keying. So now we'll substitute here. What is energy difference? The energy difference between the signal, which is nothing but S1 of t minus S2 of t whole square integral 0 to t. Therefore, we'll write directly. Now integration 0 to tb S1 of t minus S2 of t, which is A cos 2 pi FCT whole square dt. So this is nothing but A square by 2 integration dt is tb plus this is a cos over a period is this is 0. So this is the energy difference between the signal. So can I substitute here? Yes, this is nothing but q of square root of A square tb by 2 into 2, this is 4 n0. This is the probability of error of ASK. This is the probability of error of what is this? This is the probability of error of ASK signal, amplitude shift keying signal. Note down. Now the TSK signal. Now phase shift keying signal S1 of t, which is equal to A cos 2 pi FCT Now this is for binary 1. For binary 0, S2 of t, which is equal to minus a cos 2 pi fct. Now this is for binary 0. So now the energy difference between the signal ED, which is equal to integral 0 to Tb S1 of t minus S2 of t, a cos 2 pi fct minus minus plus 2a cos 2 pi fct whole square dt. Now which is nothing but 2a square 4a square by 2 integration dt is Tb plus this is 0 over a period. Therefore this is nothing but 2a square into Tb. Now this is 2a square Tb. Now this is the probability of error. Now which is nothing but Q of square root of a square Tb, 2a square Tb by 2 into n naught. Now 2 cancel, which is nothing but square root of a square Tb by n naught. Now this is the probability of error of PSK signal. Probability of error of PSK signal. Now similarly can be calculated probability of error of FSK signal. Now this is the frequency shift keying. S1 of t is a cos 2 pi f1 into t, a cos 2 pi f1 into S2 of t is a cos 2 pi f2 into t. This is for binary 1, binary 0. Now the energy difference between the signal ED, which is equal to S1 of t minus S2 of t, a cos 2 pi f1 into t minus a cos 2 pi f2 into t whole square dt over the limits 0 to t. Now this is nothing but the energy difference between the signal, how much it is from here, a square by 2 into Tb plus a square by 2 into Tb minus 0, which is nothing but a square Tb. So this is the energy difference between the signal, now which is nothing but now Q of square root of energy difference a square Tb by this is 2 n naught. Now this is the probability of error of FSK signal. These are the probability of error of a different digital signals, digital modulated signals, now which we are calculating. Okay, note down this. Okay. Now, on-off signaling. In on-off signaling, S1 of t is plus a, S2 of t is 0. This is for binary 1, this is for binary 0. Now what is the energy difference? Energy difference, now a minus 0 whole square over the limits 0 to Tb dt, which is equal to a square Tb. Now this is the energy difference between the signal. So which is nothing but now Q of a square Tb by 2 n naught. This is the probability of error of on-off signaling. Now similarly, a probability of error of non-return to 0 signaling. Now this is a non-return to 0 signaling. Now for S1 of t is positive voltage for binary 1 and S2 of t is minus voltage for binary 0. So what is the energy difference? The energy difference integration 0 to Tb S1 of t minus S2 of t a minus of minus a whole square dt, which is equal to integral 0 to tb 2a whole square 4a square dt. Now which is equal to 4a square tb. Now which is nothing but probability of error, which is equal to q of, which is 4a square tb by 2n naught. So which is nothing but this 2 to cancel. Now this is 2a square tb by n naught into probability of error of non-return to zero signaling scheme. These are the probability of error of any digital scheme. Now this is the formula. You just see this one, you can get a more clarity. Now the probability of error is depends upon signal strength, bit duration, noise power. Signal strength, bit duration, noise power, spectral intensity. Signal power, bit duration, noise power. Therefore, it depends upon the signal strength as well as how much is the duration of the bit, and it depends upon the signal power and the bit duration, and obviously the noise effect is common for all the signals. Okay. Now we'll see these are the three digital modulation techniques. Now we'll see now which probability of error will be. Now these are the probability of error or bit error rate. These are the probability of error or bit error rate of a different binary signals, right? And this is also called as bit error rate. Bit error rate. Now you tell me probability of error of ASK, which is equal to Q of 1 by root 4 1 by 2, which is equal to Q of 0.5. Let us assume A equal to 1 volt, bit duration TB equal to 1 second, and a noise power N naught, which is equal to 1 watts. All are normalized value. 1 1 1 root 4, 1 by root 4 is 1 by 2, 0.5. Now the probability of error of PSK, which is equal to Q of 1 1 1 root 1, which is equal to 1, which is equal to Q of 1. Now the probability of error of FSK, which is equal to Q of root 1 1 1 1 by root 2, Q of 1 by root 2, which is equal to Q of 0.707. Now if you see here, you already know that now when X is maximum, Q of X is minimum. So here 0.5, 0.7, which X is maximum? This X is maximum. Therefore, this probability of error is minimum and this Q of X is minimum. Therefore, a probability of error of PSK is the least one, right? Now, after that, which X is maximum? This X is maximum. Therefore, probability of error of FSK. You know that when this X value is maximum, Q of X is minimum, probability of error is also minimum. Therefore, now here this X value is minimum, therefore this probability of error is maximum. So the probability of error of ASK is the highest one. And you already know that. Now what is the bandwidth? In the digital modulation techniques we will covered here. Here bandwidth is twice of the bit rate. Here bandwidth is twice of the bit rate. Here bandwidth is twice of the bit rate plus Markov space frequency difference, right? Now the reason you know that, now this is having highest probability of error, even a bandwidth is less, therefore this will not take it. Now this bandwidth is more, probability of error is less but bandwidth is more, that is the reason why this is also not considered. But here bandwidth and probability of error is minimum, that's why most of the digital communication systems, the modulation, most of the digital signals are modulated with the help of analog carrier, and that modulation technique is ASK, FSK, PSK, but the best one is PSK is preferable. Okay. Now here, now we'll see the classroom workbook question. Now the classroom workbook question number 1. What is the question number 1? Now a received non-return to 0 signal Now see here, non-return to 0 signal means this one, right? Now a received non-return to 0 signal assuming that the voltage levels of 500 millivolts for binary 1 and minus 500 millivolts. Now this is minus 500 millivolts for binary 0. The signal is affected additive white Gaussian noise whose two-sided power spectral density of the thermal noise is 10 power minus 6 watts per hertz. The received signal is compared with the threshold comparator and determine the bit rate, and he is giving one clue for you. Probability of error, now he is given one clue. The probability of error which is equal to 10 power minus 5. Now he is given probability of error equal to 10 power minus 5, Q of x which is equal to 10 power minus 5 when x equal to 4.27. Now you know that the probability of error of non-return to 0 signaling scheme is how much? The probability of error of non-return to 0 signaling scheme is in terms of Q function, which is Q of A square TB by N0 by 2. This is nothing but, this is the probability of error of Q function non-return to 0 signaling scheme. This 2 I can write it here. Now which is equal to, how much is given? This is also given. Now Q of x which is equal to 10 power minus 5. Yes, this is Q of x. Q of x equal to 10 power minus 5, but when x equal to 4.27, but what is the x here? The x here is, sorry, this is under root. All these are under roots. Sorry, all these are under roots. Okay, root of. So therefore this is root of. Now root of A square TB by N0 by 2 which is equal to 4.27. Therefore now what is A? A is 500 milli which is equal to 10 power minus 3 by N0 by 2, two-sided power spectral density 10 power minus 6, square both sides, the root is cancelled, therefore 4.27 whole square. From here you can get one unknown parameter which is nothing but TB. So here you can get one unknown parameter which is nothing but TB. Now you will find TB here. Now bitrate. Now bitrate RB which is equal to 1 by TB. Now this is the bitrate which is equal to now 1 by TB, now bits per second. From here you find TB and you substitute that, then this is the bitrate. Okay, note on this.